So it is a great honor for me to introduce Professor Keshav Pingali from the University of Texas, Austin. Keshav is the first distinguished speaker for the series of a CS distinguished speaker series this year. And Keshav is a full professor at UT Austin and is one of the top researchers in the area of parallel programming languages, compilers, and systems. He is a fellow of ACM, IEEE, and AAAS. And actually, he has served on important programming committees. He was actually the program chair of last year's PLDI, and he was the chief editor of the Topless Journal, which is the best journal in the area of programming languages and systems. And Keshav is going to talk about his recent work on the Galois system, which is a new programming language system for parallel programming. And this system has led to a series of important papers in top-notch conferences in programming languages and systems. So with that, I'd like to welcome Keshav.
Thank you. Thank you for that kind introduction. Well, it's a great pleasure for me to be here. This is my second visit to UC Irvine. I was here many years ago when I was a graduate student. So as you can tell, that must have been a few decades ago. So I do have a small connection with Irvine. My PhD advisor was Arvind, who's at MIT. And he was actually a faculty member in your department for several years. And so there was a workshop on data flow at Irvine, and he said, hey, you want to come to Irvine? And you know, back when you're a graduate student, you're willing to go anywhere, right, with your advisor. And so I was here for a few days, and it always struck me as a very beautiful place, a wonderful place to live and to do research. So I'm very pleased to be back here after a few decades. Thanks again for inviting me. So I'm going to talk about a bunch of things, but mainly about graph analytics, and also about the Galois system, which, as Harry mentioned, is a system that we've been working on for about 6 to 7 years since I moved to UT Austin. It's targeted for irregular problems, graph problems, but as I will try and argue, it's actually good for other kinds of problems as well. So it's a general parallel programming platform that we have developed, and at this point we have users in several places. And so what I'm going to tell you about is graph analytics, how to think about parallelism in graph analytics, and how we use the Galois system to simplify the programming of graph analytics problems. So let's begin by talking about parallel computing in general. So as a community, we've been working on parallel computing for many decades now, probably about 40 years or so. The field got its start in places like Illinois with the pioneering work of people like David Cook, for example, who back in the 60s started talking about vector computing, and then later they started working on things like parallel computing. And we've been working on parallel computing ever since. But in the past 10 years or so, 5 years, 10 years, there's been an enormous change that has happened in our field. And that's what I want to begin my lecture by telling you about. And so I'm going to call it the old world of parallel computing, and then this new world of parallel computing. So why did people start working on parallel computing? Well, back then, parallel computing was used mainly by computational scientists. So there were physicists and chemists and people like that, or engineers. And what they wanted to do was to solve partial differential equations. Well, for most PDEs, you can't solve them exactly as you know, so you use numerical methods. These numerical methods lead to large computations, usually iterative solvers. And so what you need to do is you need parallel computing in order to solve these kinds of computational science problems. And so things like fluid flow, at this point, if you ride on a 777 or any of its successors, right, all of those planes are actually designed mostly on the computer. They do a small number of wind tunnel tests just to make sure that the simulations are okay. But really, it's all about computational science and using that to design things like airplanes. For the most part, in what I will call this old world, this more traditional view of parallel computing, the data that we use is what I'll call structured data. So we're talking mainly about things like vectors, And matrices, these matrices are dense, but they could also be sparse, but really very structured data. In the new world, things are totally different. In the past 5 to 10 years, what has happened is the social media has become extremely important. And so we have all kinds of machine learning and big data problems that people are trying to solve. And again, because of the scale of the problems, people are using parallel computing. In this new world, really most of the data is what we're going to call unstructured data, so large graphs. Now you can look at a lot of large graphs really as sparse matrices as well, but in these graphs that are useful in social media, what happens is you add and remove nodes and edges constantly. And so the graph is very dynamic in structure, and that's kind of hard to model using sparse matrices. It's much more convenient to think about it as an unstructured graph. So this is a change that's happening. It's a big change. So in the structure of the data. A second big change that's happening is in the platforms on which we're doing parallel computing. So in the old world of parallel computing, what you had were these dedicated clusters. So at the University of Texas at Austin, where I work, we have TAC, the Texas Advanced Computing Center, which has one of the largest open machines in the world. And so these are machines that are dedicated to this old style of computational science problems and so on and so forth. In the new world of parallel computing, really it's a much more heterogeneous, complex, dynamic platform. So you have basically a client-server kind of model. And so you have a lot of computations going on in servers in the cloud. But then there's also a lot of parallel computing that needs to happen on your cell phones, right? So that's the client. And so mobile plus cloud. And so this gets to be very complicated because even on your cell phone, you have a bunch of multi-core processors, you have a bunch of GPUs, and so there's a lot of parallel computing that's actually being done over there. Every once in a while, it communicates to something in the cloud, a big server somewhere, so there's computing that goes on there as well. So it's a much more dynamic, complex platform than the traditional old world picture. And then the final change, and this is what interests me as a parallel programming person, as a programming languages researcher, is in the change that's happening in the people who want to write parallel applications. So in this old world, what you had were a bunch of people in the national labs who would develop a code for 10 years, and then they would spend their entire career, for example, maintaining that code. So there were a small number of these ninja programmers, right, who were experts in a particular application, they were experts on a particular platform, and they would spend their lives essentially developing and maintaining that code and becoming very expert parallel programmers. Today, however, because of the commercial importance of all these social networks and social media and so on and so forth, everybody is trying to do parallel computing. They're all trying to implement these kinds of algorithms, which I'm going to tell you about in a minute. I'm going to give you a couple of examples just to focus the discussion. But these algorithms on these unstructured graphs, and they're trying to do it on these big, complicated platforms, and they're really sort of operating out of garages and things like that. So these are not expert parallel programmers who devoted their lives to parallel programming, but large numbers of self-trained parallel programmers. So there's a change in the style of data that we're using, change in the platforms, and then above all, a change in the people who are trying to write parallel programs. And so what my talk is going to be about is essentially about how we're designing the Galois system in order to appeal to the new world. The old world is still going to be important, but this new world is increasingly important, and so we're targeting that sort of an application area and those kinds of programmers. And so I'm going to refer back to this throughout my talk. So to understand this change, let's take a look at a couple of applications. And I'm going to do these applications at a cartoon level. So you shouldn't take the algorithms too seriously, but it'll give you a flavor for the kind of computations that people want to do. And the first example I want to pick are these friend recommendations that are constantly made. So if you're on Facebook, for example, every once in a while, you'll get a recommendation saying you may want to become friends with some person or the other. So, most people my age don't have Facebook pages, but I finally broke down and ended up getting a Facebook page. And at this point, I have 26 friends. And I was telling my daughter this. I said, I have 26 friends. And she looked at me and said, do you know the average person has about 350 friends? Okay, well, I think 26 is enough for me. But so, how do these friend recommendations work? Well, you have basically for Facebook what is called the Facebook graph. It's a graph in which the nodes represent people, the edges represent the friends relationship. And so let's say you have some person U, and U is friends with A and B are friends with V and W, and so on and so forth. So obviously you can think about this as an unstructured graph. At this point, there are roughly about 1 billion people. So it's a graph with about 1 billion nodes. And if we say that the average person, if my daughter is right, and the average person has 300 friends, well, there's a fan out of 300 from each of these nodes on the average. Okay, so now how does Facebook decide who to recommend as friends to you? Well, the first question is, how do you find candidates for friend recommendations? And then the second thing is, how do you rank them in order of importance, right? So here is one way of finding candidates. What we do is, we say, well, if we're trying to recommend friends to you, maybe a good thing to do is to find friends of friends, right? Who are not already friends of you. So who are the friends of A? Well, the friends of A are U, B, and V. Well, we're going to assume you're your own friend, so we don't need to recommend yourself to you. We assume you already like yourself, right? So fine, we don't worry about you. B, well, B is already a friend of you, so we don't need to worry about B. But V is somebody that perhaps we could recommend to you. And in the same way, we can recommend W. Now, if you think about it, if there's a fan out of 300, well, 300, right? And then 300 more, well, that's a lot of candidates. And obviously, if Facebook keeps flooding you with lots and lots of recommendations, most of them will probably be useless. What needs to be done is to rank these suggestions to you. And so what they do is to use a bunch of ranking functions. So you can think of structural things like looking at the number of mutual friends. So V, for example, has 2 mutual friends with U as opposed to W. So perhaps V is more likely to be somebody that you want to be friends with. But actually, Facebook knows a lot about you. They sometimes know more about you than your own parents do, right? Usually that's the case. And so there's a lot of attributes on these nodes, such as, for example, what your interests are and so on and so forth. And so they try to match you up with people that they think might be your friends. But this is the basic idea. So you use the graph structure to find some candidates, and then you use other information in order to rank the candidates, and then you give some subset of that list as recommendations. So that's the key takeaway. So the key data structure is a large sparse graph. It's constantly changing, mutating as people are entering the system, making friends, leaving the system, and so on. And then the algorithms may involve part computations from the graph. Basically, you do a breadth first search, you go 2 levels out, right? That's essentially the kind of computation that's going on there. Here's another one that you're probably familiar with, and I'm going to go quickly over that. So this is the famous PageRank computation. So this is how Google sort of got its start. So at the long time ago, when the internet first started, right? So how did, if you typed in a query to something like Yahoo, well, so you said sports, right? So I want a bunch of pages that deal with sports. So how was that done? Well, it turns out that the way it was done was manually. So at Yahoo, there were people who actually went, browsed the net, looked for sports pages, and then they made up like yellow pages, right? So they had lists of pages that were dealing with sports, and so then if you typed in a sports query, then they gave you those pages ranked in the order that somebody at Yahoo thought was a useful ranking of web pages, right? But this is obviously not a very scalable thing. So as the internet started growing, people realized you need an automatic algorithmic way of making these responses to these search queries. And so here is essentially the way that it's done today. What you do essentially is, once again, you build a graph, except that in this case, the nodes are web pages, and then the edges in this graph are these hyperlinks between web pages. So if I have a web page that has a link to your page, well, then there is a directed edge from my node to your node. And so you can see U and V. So U essentially has some edges, some hyperlinks to those 3 web pages, including page V, and then there are some incoming edges because there are other pages that are referring to U. So once again, you notice you have a graph. Again, it's a very dynamic graph because there are web pages that are being created, removed, adding links, removing links, and so on and so forth. And here is how essentially this famous PageRank algorithm works. And I've simplified it greatly just to give you a flavor of what happens. Essentially, what you do is you use something like citations, right? So if you're looking for an important paper, you look at the number of citations that that paper has. However, it's easy to spoof a system that just looks at the number of incoming edges, because I could add a whole lot of dummy web pages, right, that all point to a particular web page that I want to see promoted. And then it's like self-citations, right? I cite a lot of my own papers, and so, well, then the citations go up, but then perhaps that's not as useful as a paper that's being cited by a lot of other people. And so the PageRank algorithm essentially was developed to avoid this sort of spoofing. So what you do essentially is the following. The algorithm works in a bunch of super steps. Initially, what happens is you initialize the weight on each node to 1 over n, if n is the number of nodes. And when the algorithm terminates, the weight on the node is a heuristic measure of the importance of that particular node or that web page. And so what happens in each super step is the following. So you will have some particular weight on it, and what it does is it divides its weight equally and contributes that to each of its outgoing neighbors. So in this case, whatever weight is there on you is divided by 3 because it has 3 neighbors, and then that is added to the weight on the nodes that it points to. So if I look at it from the perspective of a node, what happens in each super step, which I'm going to call the I plus first super step, is you take the weights that are currently computed in the ith step, and then you essentially have a contribution that you need to add up from your neighbors. So it looks like this. You take the page rank of all your in neighbors divided by their degree, and then you sum that up. And there are a few other things that you need to do, but this again gives you a flavor of the kind of computation that's going on. Is the battery dead? I think the battery is probably gone.
Is there a light? Doesn't work as well.
Can you hear me at the back? Yeah, I have a voice that usually carries, but if you're recording this, that may not work. I'm good? Okay. Well, apparently I'm okay, so let's just keep going. We're going to be fault tolerant here. Right? Okay, so here is the core algorithm. And again, the details are not terribly important, but I wanted to give you a flavor of this algorithm. Essentially what you're doing is you have weights on nodes, and then you're updating the weight on a node depending upon the weights on its neighbors, and then you keep doing it until some convergence criteria. Okay, so you can carry that out for this particular example, and then when the algorithm terminates, those are the weights that you're going to see. And the thing to note is that even though B and E both have a lot of incoming edges, right? So both B and E are being pointed to by a lot of other nodes. Notice that E is being pointed to only by nodes that are not themselves being pointed to by other nodes, and therefore its page rank is less, right? So that's the basic idea. Okay, so that should give you the flavor of these kinds of algorithms. Good, so now what is the programming language problem? Here's the programming language problem, and this is what I'm going to call the search for scalable parallel programming models. And by scalable here, I don't really mean scalable in the sense of parallel performance, getting more performance as you increase the number of nodes and so on. Really by scalable, what I mean is going back to this point of view that parallel programming for these kinds of graph applications is now going to be done by lots and lots of people. And so whatever programming models that you build, systems that you build, need to be scalable to large numbers of application programmers who are not themselves experts in parallel programming. So this is what we call the tension between productivity and performance. And in our group, we divide programmers into 2 classes. The vast majority of application programmers who are not parallel programming experts, we're simply going to call them Joes. Okay? And so there are going to be lots and lots of Joe programmers. And then there are a small number of very expert parallel programmers, and we call them Stephanies. And so our role as Stephanies, as parallel programming experts, is to build systems in a way that can be supported, that can support large number of Joes, right? That's essentially the problem for us. Okay, so how do you hide complexity? That's essentially what we need to do. How do you hide the complexity of the underlying parallel programming platform? Well, there's only one way I know for hiding complexity, and that is to use abstraction. So we need to build abstractions and then implement those abstractions in an efficient way so that we can support this ecosystem where there are a large number of Joes. So the question, of course, is where does one draw the line? So if you draw the line very high, then, well, that's good for Joe, right? Because the abstractions are now very close to the problem domain. However, our job as Stephanie's becomes extremely hard because now we need to find a way of producing efficient parallel code out of programs written at a very high level of abstraction. So that's kind of difficult. If, on the other hand, the line is drawn relatively low, like we say, well, go program in p-threads with locks and so on and so forth, well, our job is very easy, but obviously that's not very scalable to large numbers of relatively naive parallel programmers. So that doesn't work either. So the search for scalable parallel programming models then is, where do we draw that line, that golden median, so to speak, so that we simplify the job and support millions of people who want to be Joes in this world. However, we can still build efficient, generate efficient code out of their programs. That's essentially what we need to solve. So in the Galois project, we have a particular place where we draw that line, and I'll tell you about that later. But here is the key idea. So what we have are what we're going to call data-centric abstractions. That term is not going to mean anything to you right now, but that is one of the key insights that we've had, as opposed to the program-centric abstractions that people have used for the past 30 to 40 years. So we have certain data-centric abstractions, and those help us to decide where that abstraction boundary should be drawn. We've implemented those abstractions. We have what we think is a reasonably scalable shared memory system. So we've gone up to 512 cores, which is a reasonably sized parallel machine. And we've solved graph problems with 100 million nodes, 2 billion edges. So we're not talking about Facebook-size graphs, but really for most applications in this domain, that turns out to be large enough. Okay, now you're probably used to academics coming and telling you, oh, you know, we built this system and it's wonderful and so on and so forth. So what I want to show you is a study that was done at Intel. So this is a paper that appeared at SIGMOD last year. So it's from Pradeep Dubey's group. What they did was they took a bunch of graph problems. So one of them was PageRank, which I told you about, and then the other is breadth-first search, and you already saw why breadth-first search might be interesting. They found about 5 of these graph applications. They took a bunch of different graphs. So this is a portion of the Facebook graph, and then some other graphs over here. And what they did was they wrote programs for these applications in a bunch of graph frameworks. So this leftmost line over here is what they call native. So native just means pthreads, OpenMP, so some low-level programming notation. The rightmost line is the Galois line. So that's the red line over here. So you write that in these abstractions that I'm going to tell you about. And then in between are a bunch of popular graph frameworks. So I'll just talk about GraphLab. So GraphLab came out of CMU. It's now at UW, Carlos Gestrin and company. It's very popular in the machine learning community. So that's GraphLab. And Socialite is from Monica Lamb's group at Stanford. So there are a bunch of these graph frameworks that they took. What they did was to implement these algorithms in these frameworks, and then they evaluated performance. The y-axis is time, so lower is better. And then what you notice, if you go across over there, is essentially the performance of these Galois programs is roughly comparable to what you get if you program in a lower level notation like pthreads. And we are substantially better than most other systems. So Giraffe over here is the Facebook system for doing graph algorithms. It's based on Hadoop, so it does a lot of I/O and so on and so forth. So perhaps the comparison is not particularly fair, but these are their numbers. So giraffes have long necks, and so as you can see, these lines have long necks. So notice that this is actually a log scale, so you know they're really thousands of times slower than us. But even if you compare against GraphLab, for example, which is a fair comparison because they don't do any disk I/O or anything like that, for a bunch of these applications we're orders of magnitude faster than them. So now that I've established some street credibility over here, right? So let me tell you more about what we do inside the system. Let me begin by giving you what we've learned as we built this system. And this is like the one of the messages that I want to give you. So we've learned a lot about abstractions for parallelism. We've learned a lot about parallelization strategies. We've also learned a lot about how to write applications. And this sort of distills out what we've learned. So yesterday and today, yesterday is that old world style of thinking that I started my talk with. So in the old world style of thinking, what we dealt with were computation-centric abstractions. And by that I mean, when we looked for parallelism, we looked at loops, or we looked at procedure calls, and then we said, could we do these loops in parallel? Could we do these procedure calls in parallel? That's the way we thought about it. It turns out for these graph algorithms, this new world, really we need data-centric abstractions. And it's something that I call the operator formulation of algorithms. I have a couple of slides on it. That's one of the key takeaways. And so you'll see that on the next few slides. Another thing that we've learned is about parallelization strategies. The old style of parallelizing programs, you thought in terms of a compiler looking at a program and then determining what could be done in parallel. So it looked for loops, it tried to figure out whether those loops were parallel or not, and that's how we thought about parallelism. And we were aware that there were a whole lot of other parallelization strategies, such as speculative parallelization or thread-level speculation, if you know what that is. But we thought those were things that were only needed when you didn't have enough information about what was really going on. But if you really knew what was going on in the algorithm, the compiler would be able to build a dependence graph and then schedule the parallelism for you. What we do today is something totally different. What we've come to realize is it's really speculative or optimistic parallelization that needs to be the baseline. And static parallelization really is possible only for certain kinds of algorithms that have enough structure. And I'm going to talk about that also as we go along. The final thing that we've learned is about how to write applications. So the way we thought about applications in the old world was we took the application, it might be 1 million lines long, we built a big interprocedural data flow graph, and then we did analysis on the whole thing. So we thought about programs as monoliths. Today what we've realized is programs must be layered. So data abstraction is essential, not just for software engineering, but even for parallelism. Now these are all high-level ideas. They're not necessarily going to make a whole lot of sense to you right now, but I want you to keep this in mind as we go, because now I'm going to have a bunch of examples that illustrate what these points are all about. And so the first thing is about how to think about parallelism. So here is the old style of thinking about parallelism. So here is a piece of pseudocode over here. And the kind of question that we asked ourselves was, well, where's the parallelism in that code? Okay, so where's the parallelism in that code? So, well, there's a loop over there. Yeah, okay, there's a while loop. So now what we can do is we can do dependence analysis of that loop. And if you don't know what dependence analysis is, well, then you should take Alex's course where I'm sure he talks about these things. But essentially what you do is you analyze the body of the loop to try and see whether you can do all the iterations in parallel or not. And if not, whether some of them can be done in parallel. So you build a dependence graph, and then that's how you do the parallelism. That's essentially the idea. So you use the compiler to look for loops, analyze those loops, find the parallelism. That was the idea, okay? All right, well, people developed a whole lot of static analysis compiler techniques for analyzing these kinds of programs. So if you know points to analysis, shape analysis, well, those are all techniques for doing dependence analysis for these kinds of programs. So it's what Harry did his PhD thesis on, right? So very useful stuff. But all of those techniques would come back for this particular application, and they would say, oh, there's no parallelism here, because all the iterations could be dependent on each other. So you're forced to execute these iterations one at a time, right, sequentially. There's no parallelism. That's what the analysis techniques would say. And so then in our community, there were two schools of thought. So some people said, well, maybe there's no parallelism in these kinds of applications. But other people who were smarter said, oh, you know what? What we're going to do is talk to the NSF and get them to fund more proposals, to do more research on static analysis techniques, because if we had better analysis techniques, we may be able to find more parallelism and so on. And so, I used to do both things. And so that went on for a while. The question though is, are those two schools of thought right, or are we looking at the problem the wrong way? So today, what I've realized is we were actually looking at the problem the wrong way, because rather than look at parallelism in this computation-centric way, where we looked at loops, we tried to do dependence analysis and so on, we need to think about parallelism in a very different way, and that is what I call the data-centric view of algorithms. So here's what this algorithm actually does. It turns out this algorithm is something called Galois mesh refinement. Exactly what that is doesn't really matter. But the input is a triangular mesh. So you can see a bunch of triangles. Now some of those initial triangles are badly shaped according to some shape criteria. And it doesn't matter what it is. You can look at the triangle, and let's say if it's too big, it's a bad triangle. So we mark it red. And otherwise, it's a good triangle. The goal of this particular algorithm, mesh refinement, is to get rid of all of those bad triangles and produce a mesh that only has good triangles. That's essentially what we want to do. And the way that this algorithm works is the following. It picks a bad triangle. So it picks one of these red triangles over there. Now let's see if this demo shows up. It doesn't show up over there. So I'm just going to talk you through it. So what you do is you pick any one of these bad triangles. So we'll pick that triangle, for example. Let's say the top one over there. And what you're going to do is replace it with some smaller triangles. That's why it's called refinement. But if you just do that, it turns out it violates certain geometric conditions that all the triangles need to satisfy. So what you actually do is you find all the triangles that are going to be affected, which are said to lie in the cavity of this bad triangle. So those are shown in blue. So you find all of those triangles, you remove all those triangles, and then you replace them with new triangles, like here. Now, some of these newly created triangles may themselves be bad, but there's a guarantee that if you just keep doing this long enough, you're going to get a mesh without any badly shaped triangles. Okay? So that's the idea. You go to a bad triangle, you expand its cavity, which is a small region of the graph, you remove all those triangles, replace them with new triangles. Okay, so now you tell me, is there parallelism in this algorithm? Can you imagine doing this refinement process in parallel? Okay, you're nodding your head,
yes.
So tell me why.
So if you can find the badly triangle, then you can find the cavity, and then the cavity might disjoint, then you can just work on it.
Okay, very good. So what you're saying is, if I can find some triangles whose cavities don't overlap, well then I can obviously do those in parallel. If on the other hand the cavities overlap, I can do them in one order or the other, but I can't do them in parallel. So that's really all there is to it. So in a big mesh, there is actually a lot of parallelism. And as I will show you, we've scaled this particular algorithm to 512 cores. So there's lots and lots of parallelism over here. However, if you think about it, this parallelism is not something that a compiler will ever be able to find. Because if you think about that code, each iteration of that loop was fixing one of these triangles. And essentially, when you're asking the compiler to tell you what you can do in parallel, you're saying, I'm not going to tell you the input mesh, I'm not going to tell you what's happening to the mesh, but I want to know, are the cavities of these two triangles overlapping or not? Well, the compiler obviously does not have the runtime information that's needed to make that decision. So this is something, there is parallelism here, however, the parallelism can only be found at runtime while executing the program. And in fact, that's what we do in our system. So here is the key idea. The computation that I'm going to do at a bad triangle, I'm going to call an operator. So just think of that as a computation that's done at that bad triangle. That needs to happen atomically. It just needs to happen as though it was the only thing happening in the system. Now, the second thing that you need to think about is the scheduling. In general, you have lots of bad triangles. So if I have only one thread, you need to figure out which triangle to work on next. Right? And you can imagine many different ways of doing this. You can keep, for example, a queue of bad triangles. Or you could keep a stack of bad triangles. Or you could just randomly pick triangles. So these are what we call different schedules. And it turns out, if you maintain this work list as a stack, then you get locality. Because when you fix a bad triangle, you create some new bad triangles, you put them on the stack, and you work on them right away. And so there's a good chance that you already have a lot of the working set of the triangle over there. So you get a speed up of 2 just by using a stack, right? By using LIFO scheduling rather than FIFO scheduling. Okay, so now here is the motto that we have in this data-centric way of thinking about algorithms. So an algorithm is an operator plus a schedule. So the operator is this action that you perform on the data structure, and then the schedule basically says when these operations are done on different of these active elements or active triangles, as we call them. Okay? Now, in addition to this way of thinking about the algorithm, notice that we also need some parallel data structures. So in particular, we need a work list of these bad triangles that different threads can go to, get bad triangles from, put bad triangles, newly created ones, onto. It turns out that if you look at it this way, the most difficult part of implementing this algorithm is actually implementing this work list of bad triangles, because unless you're very careful, that work list ends up becoming a bottleneck, right? Everything else doesn't matter as far as performance. Just going to the work list and getting work out becomes the bottleneck. In our system, we spent roughly 1 year instrumenting, working on this particular work list in order to do it right. So the main difficulty in parallel programming, if you look at it our way, is really in these parallel data structures, getting these parallel data structures done efficiently, as opposed to implementing this algorithm itself, which turns out to be relatively easy. And that's very different from what you're taught in parallel programming courses, because usually we say, oh, we should teach students parallel algorithms. Well, the algorithms are actually not all that hard. It's really the data structures, getting the data structures right, that turns out to be the main difficulty. Now, I promised to talk about graph analytics, so you might be wondering, how is that algorithm equals operator plus schedule motto that I showed you, why is that relevant to graph analytics? It turns out that particular way of thinking about algorithms is actually a very useful way of thinking about all algorithms, not just the algorithm that I showed you, the mesh refinement. So here is a problem that I'm sure all of you are familiar with, single source shortest path. Right? So it's probably the first graph algorithm that many of us are taught. So here is the essential problem. I give you an undirected graph. So the nodes might represent cities, the edges represent roads, so there are various distances. One of them is a source, so that is A. And what I want to do is compute the shortest distance from A to each of the other nodes. So that's the famous single source shortest path problem. Now, if you open up a textbook and you say, give me some algorithms for this book, well, you see a bunch of seemingly unrelated algorithms. So you've probably heard of Dijkstra's algorithm, right? Everybody know Dijkstra's algorithm? Raise your hand if you've studied Dijkstra's algorithm. Okay, so what's the key data structure that's used over there? A priority queue, right? Yeah, so it's based on a priority queue. Then you have Bellman-Ford, which you've probably learned, chaotic relaxation, delta stepping, which is a parallel algorithm. So these look like very different algorithms that don't really have anything to do with each other. It turns out, if you look at it in terms of my motto, algorithm is an operator plus a schedule, something very nice happens, which is you realize the common structure and you also understand the differences. So here's the common structure. The way all these algorithms work is the nodes are, the distances are initialized to infinity. So you don't some large value other than A. And then what you do is, here is the operator for this particular algorithm. It's called the relaxed edge operator. And essentially the way the relaxed edge operator works is, if you look at AB, for example, the distance of A is 0. So if you add 0 to 5, you notice that 5 is less than infinity. So you can update the distance label of B and lower that to 5. So that's called the relaxed edge operator. So here's how all these algorithms work. Let's say that an active node is an unprocessed node whose distance field has been lowered. So we've lowered its value, but you haven't yet looked at it. So you have some active node, just like you had those bad triangles that were sitting there in the mesh, saying, please come and fix me. Similarly, over here, you have nodes saying, some thread, please come work on me. Apply the relaxation operator there. So initially, only A is active. So a thread comes and applies the relaxation operator there. So now you have B and C, whose distance labels are lowered to 2 and 5. Okay, so now 2 and 5 are active. Now, if you have only one thread, you need to make a choice. Do I work on B or do I work on C? So let's say that I work on B. So what happens when I apply the relaxation operator there? I'm going to reduce the label on D now to 12. So now D becomes active. So now I have C and D. When I apply the relaxation operator D, I'm going to lower the values on E and F. So I'm going to propagate a whole lot of values in there. And then at some later time, I'm going to relax this edge So I'm going to lower D down to 3, and then I'm going to have to work on that subgraph all over again. So I'm going to do a lot of work, additional work. So what's a better order in which to do things? Well, if I worked on C first rather than B, then I would relax the values in that subgraph only once rather than twice. So what that says is, what you should do is take your active nodes and sort them by distance and always work on the smallest one. So what algorithm is that? That's Dijkstra's algorithm, right? Because that's essentially what the priority queue does for you. So that's just one particular schedule. This first approach that I showed you, where you just randomly picked active nodes, so that's called chaotic relaxation. And then Bellman-Ford and delta stepping just turn out to be other schedules that people use. So different schedules basically differ in parallelism, locality, and work efficiency. So they all have the same operator. They just have different schedules, and if you use different schedules, you end up with different algorithms. So again, you see that same motto over here. Algorithm is operator plus schedule. And it turns out you can look at the old style algorithms like finite differences, and again, the same sort of way of thinking about algorithms emerges. An algorithm turns out to be an operator plus schedule, and for lack of time, I'm going to skip over that and just show you the key abstraction now. This is the takeaway from those discussions. So this is what we call the operator formulation of algorithms. It's a way of thinking about algorithms in terms of operations on data structures and not in terms of loops, procedure calls, and so on and so forth. So in all these algorithms, there is the notion of an active element. So these are nodes or edges where computation is needed. The operator is this computation that you do on an active node. So that is just some atomic computation that needs to happen at an active node. When you apply the operator to an active node, it reads or writes a small region of the graph. That's what we call the neighborhood for this particular activity. So it's like the cavity when I talked about mesh generation, for example. Okay. And then, as we said, in general, there are going to be multiple active nodes. So then you need to decide what order to do these active nodes in. And so that's where the schedule comes in. And in most of the algorithms we're going to talk about, in principle, you could process these nodes in any order at all, and you get the correct answer. However, some schedules, some orders are going to be more efficient. Some of them will give you better locality, more parallelism, and so on and so forth. And so this is what we call amorphous data parallelism. And this is the parallelism that shows up in these graph analytics algorithms, among other places. So multiple active nodes can be processed in parallel, subject to the constraint that these neighborhoods should not be allowed to overlap. And so here is our motto. A parallel program is an operator plus a schedule plus a parallel data structure. The parallel data structure, one example of that, is this work list that you need to maintain of these active nodes.
So Keshav,
yeah.
I have a question. How would you compare this model with, for example, the vertex-centric computation model for the graphs?
Yes. So GraphLab has this notion of a vertex-centric computation. So the limitation there is that in a vertex program, the computation that you do at an active node can only look at its immediate neighbors. So it can't look at the neighbors of neighbors, for example. That limits the number of algorithms that you can do. So for example, in union find, you have to look at the parent of a parent, and then you have to short that. So you can't write algorithms based on union find. And I'll show you some examples of where that makes an enormous difference in efficiency. So for some problems, we're tens of thousands of times faster than GraphLab because you can't express certain efficient algorithms because you're limited to the immediate neighbors.
But they don't need a scheduler, right?
No, they do.
Because
actually.
they do need a scheduler?
Yeah, they do.
Okay.
Yeah.
How do you show the order of the scheduling of the operation in this graph, this non-directed page? So how do you know which operator to go next? Maybe I'm missing something.
So you maintain a work list of all the active nodes. Okay. And then depending upon which one you pick, that determines the schedule. So if you maintain that as a queue, then that gives you one schedule. If it's a stack, it's a different schedule, and so on.
But in your graph that you have here, I cannot, just looking at this graph, I can't see.
No, the schedule is actually part of the algorithm, not part of the data structure. So I'll show you how it shows up in the programming model. Okay, so that's the operator formulation. And now let me quickly go over when you can find this parallelism. So that depends upon when you know the active nodes and neighborhoods. So in very simple algorithms, you know all the active nodes and neighborhoods before you run the problem, right? So the active nodes and neighborhoods are independent of the input data and runtime values, so dense linear algebra, FFTs, and so on. For those, you can do compile time parallelization. In other cases, you know active nodes and neighborhoods only at runtime when you're actually executing the algorithm. So for those, you have to use speculative execution. That's one of the things we do in our system. And then there are other points where you know the active nodes and neighborhoods. For example, after the input is given, but before you actually run the algorithm. So that's what we call inspector executor. So what this approach does is to unify a bunch of parallelization strategies, but before we did our work, seemed like they were totally unrelated to each other. And I'm happy to talk about this offline with you guys. So let me show you now how all of these abstractions, insights, etc. are realized in our system. So remember, that is our motto. So parallel program equals operator plus schedule plus parallel data structure. So we said we need to determine where to draw this line between the Joes and the Stephanies. Well, here is where we draw the line. As I told you, what we've realized, and this is something that most people don't tell you about, the problem in parallel programming really is in building efficient parallel data structures. So in our system, we give you a bunch of efficient parallel data structures, such as, for example, very efficient work lists from which you can get and put work, and then you can specify the schedule in which you get input, right, in order to get different schedules. So the Stephanies, my expert parallel programming students, they build this library of these very efficient data structures. And then what you have to do is you have to use our data structures, and then you have to specify the operator for your algorithm, and then you have to tell us the particular schedule that you want. And what we do is to give you a small DSL for specifying the schedule. So it's very similar to OpenMP if you use that. But since we're dynamically creating work, so we also have FIFO, LIFO, chunking, and so on and so forth. So what you do, and I'll show you a very simple example of a Galois program, but essentially you write, this is all implemented in sequential C++. So this is where the simplification comes. You don't need to think in terms of locks, concurrency control, et cetera, et cetera. What you have to do is you write your code in sequential C++, except that you use a iterator, a set iterator called the Galois set iterator, for highlighting opportunities for parallel execution. So this is the iterator that goes over the work list of your active nodes. And so that is a way of highlighting opportunities. What we guarantee is parallel execution of these iterators, and we ensure that you have atomic execution for each of the iterations. And so here is how it's actually implemented. So here's the application program. So this is just a C++ program with that iterator shown in yellow. So there's a master thread that begins the execution of the program. When it gets to the iterator, it starts spawning other threads, and then all of them go to your work list of active nodes over here, and each one starts working on a different active node. And then as they start working, they make these API calls in order to expand their neighborhoods. So you say, give me the neighbors of the active node, the neighbors of the neighbors, and so on. What we do is all of those graph elements are locked on your behalf before they're returned to you by the API call. And if we detect a conflict because some graph element that you want is already used by somebody else, then we roll back one of the computations. So we use speculative execution over there, and that's how we exploit the parallelism here. But we also have all these other parallelization strategies that I talked about at a very high level. So that's essentially how the abstractions are implemented. Here is a very simple hello graph Galois program. All it does is walk over all the nodes of a graph and adds 1 to the value at every node. So here is main. What you do is you read in the graph from somewhere, and then you write this Galois iterator, this for each iterator, that just goes over the graph and applies that operator. So the operator is P. P over here, as you can see, takes a node, reads the value, adds 1 to it, and writes it back. So this is the operator, this is main, and then the rest of it is just declaring the graph data type. So as you can see, this is essentially sequential C++, and so this is where the simplification comes in the parallel programming model that we give you.
Can I think of operator as the update function in that?
Yeah, that's right. So what we guarantee is that that particular update is going to happen atomically, so you don't need to worry about other concurrent updates that are happening in the system. Okay, so I'm going to end by showing you some performance results just to show you this is a reasonable way of doing things. I already talked in the beginning about this Intel study, so I'm not going to talk about that. here is a study that we did that appeared in SOSP. So what we did was 2 studies. So when we tell people that we are, thousands of times faster sometimes on GraphLab and so on, they don't believe us, or they say, well, why is this, right? So here is why. What we did was we took a bunch of these graph analytics applications ranging from BFS to single source shortest path that we talked about, PRS, PageRank, and so on. And the first experiment that we did, we said, let's use any algorithm that we can write in the Galois system. And for GraphLab, what we're going to do is we're going to write these vertex-centric algorithms. So not all algorithms can be written as vertex programs, as we just talked about, but that's their problem, so to speak. And then we'll take a look at how much faster or slower we are. So that shows, these are the charts that show that. The first set of charts show you for the Twitter 50 graph, which is social network graph. The second set of charts below show you performance for a road network. And what we're showing is the running time. So this is the running time of the Power Graph program over the Galois program. So this is how much faster we are. So any number above 1 is actually good for us. And what you notice is that even on the Twitter graph, we're like 1,000 times faster for some applications. And for the road graph, we're actually 10,000 times faster very often. And that's essentially because we can express very efficient algorithms using our operator formulation that you cannot describe as vertex programs. The second set of experiments that we did was we said, let's restrict ourselves to vertex programs. And then let's take a look at the relative performance. So then what we're comparing really is how well engineered our system is compared to theirs, because everybody is using the same algorithms. But even over there, what you notice is that there are factors of 10 to 50 for many of these algorithms. So we are substantially faster because the system is also better implemented internally than their system is. These are performance numbers on an SGI ultraviolet. So the x-axis shows the number of threads, and the different colored lines are for different applications. So we talked about Delaunay mesh refinement. That's the green line over there. And remember, that was the application that before we did this work, people weren't sure whether there was any parallelism there or not, right? And what we're showing is the scaling. So this is relative performance of 1 thread versus 512 threads. And you notice that we scale to about 400. So there really is a lot of parallelism, and the Galois system is able to find that parallelism. Now, the other thing that we also did was to compare against third-party codes. And so for Delaunay mesh refinement, there is a code from Jonathan Shuchak at Berkeley called Triangle. So 1 thread, it's a single-threaded sequential code. That takes 96 seconds for this particular input. On 1 thread, we take 155 seconds. So there is a penalty that we pay because we are a parallel system. So there is some overhead over there. But then as you increase the number of threads, we scale. And so what you notice is at 512 cores, our time goes down to about 0.37 seconds. So this is substantial speed up even over somebody else's highly optimized C code, right? Sequential C code. So this is genuine speed up. Let me skip over PageRank. Here are some numbers from the design automation community. So I was at UC Riverside last year, and I ran into somebody there who said, oh, you know what, we downloaded the Galois system from your website, and we are implementing FPGA placement and routing tools in Galois. So this was we didn't know at all about this. They had just downloaded it on their own and implemented there. This is showing some routing. And what you notice is that VPR is some industry standard tool for placement and routing. And for some of these inputs, it takes 134 seconds. On 1 thread, Galois takes 145. So again, there's a small performance penalty. But then as you notice, once you go to 8 threads, you do in fact see performance improvement, a real speed up of a factor of 4 on 8 cores. Another thing that they wanted was deterministic execution. So one of the things that we have in this speculative execution model is depending on the order in which these activities get done, you could actually end up with different routes. All of those routes are legal, but every time you run the algorithm, you might get a different route. And so they said, well, could you give us a deterministic scheduler? Well, it turned out we had just finished implementing a deterministic scheduler, so we gave that to them. And what you notice is, even with a deterministic schedule, there's a small performance penalty, but you still get substantial speed up. So if you're worried about determinism, well, we know how to fix it. It's been fixed, and you can use that. So this appeared in a design automation conference paper back in, well, just last year. And they call it parallel FPGA routing based on the operator formulation, which is this thing that I've been telling you about. So this is very far from graph analytics, obviously, but what it shows you is that there's a whole range of algorithms that can be done very effectively using the Galois system. So let me finish up by mentioning very briefly relations to other parallel programming models. So this is the one motto that I want you to take away from this lecture, if nothing else. Parallel program equals operator plus schedule plus parallel data structure. And in our way of doing things, the parallel data structures and this runtime system, that's what the Stephanies give you. And then you, as the Joes, if you're the end user of our system, you have to tell us the operator and the schedule. So we talked about how these operators are like these updates to the data structures. In the functional languages community, they also think in terms of updates. So these are called rewrite rules. So if you know lambda calculus, beta reduction is an update rule. So you might wonder, well, how is their notion of an update rule different from ours? Well, in the functional languages community, the update rules are updating the program. You rewrite the program until you get what's called the normal form. Whereas for us, the update rules are really working on the data structures and not on the program. There's also a connection with transactions. So transactional memory also uses the notion of speculative execution. And so people ask as well, what is the connection with transactional memory? Well, an activity in Galois, so when you execute one of those activities, so apply the operator to an active node, that has transactional semantics in the sense that we guarantee that it operates with what is called atomicity and isolation. However, we don't have an explicitly parallel programming model like you have with transactional memory. So in transactional memory, you're taking parallel C, for example, with threads, and then you're saying begin transaction, end transaction, etc. So the parallel programming model is totally different, because for us, the Joe programming model is actually sequential C++. It's not parallel C++. And so here is the picture that we started with. So yesterday we had this computation-centric view of parallelism, this old style of thinking about parallelism in terms of loops, parallel loops, and so on and so forth, where you looked at the text of the program and you tried to find parallelism there using compiler analysis. What I'm telling you about is this different way that we do things today. It's this data-centric view of parallelism where you use this operator formulation of algorithms. It permits a unified view of parallelism and locality, which I've not had a chance to talk about, in all kinds of algorithms. It leads naturally to this Joe and Stephanie programming model, and the Galois system is one implementation of this particular motto. And where we see ourselves going with this is we're now writing DSLs on top of the Galois engine to simplify the programming even further. This is a list of the graduate students, research associates who did it. This is our homepage, so you can download our system from there. We also have a lot of benchmarks, and all our papers are there. And if you're interested in using the system, please do get in touch with us. We'll be very happy to tell you about it. So that's where you should go for more information. So thank you.
We have time for a few questions.
What's the other good for example, if this system compute on multiple machines? For example, for the 12 thread, is it on one machine?
It's one big shared memory machine. So it's an SGI ultraviolet. We are working on a distributed memory system, but that's not yet been released. So right now it's on one host.
So one in which
That's all the active nodes. And then the schedule tells you what it is to process the active nodes. You give you a small DSL. And then you write a particular schedule, make it says 5-4. Or you could say 5-4 is chunking of such time. Yeah.
You need some synchronization, for example, integration. Does that environment Galaxy environment?
That has to do from our shared data structure.
Okay, you have specific structure for those synchronization.
That's right. So you have to use our data structures because we need to know when there are conflicts, when to roll back.
So, Kashyap, I guess one question I have is that if you want to scale this to distributed systems,
Yeah.
you might have scalability issues. If you allow developers to write code to access not only the neighbors of Vertex but also
Yes.
nodes far away.
Yeah,
Right.
that's right.
I guess that's why the vertex-centric model only limits the access to.
No, the reason they limit it is just they wanted a very simple programming model,
Right.
which they thought would be adequate for these machine learning applications.
Right. Yeah, that's true.
And what we've shown is, well, it is true that there are very simple algorithms that one could write using this vertex-centric model. At the moment you want to do anything even a little more sophisticated, you really need to go beyond just the immediate neighbors.
Yes. I think
So,
that
yeah.
eventually if you run on the distributed system, then algorithm design is one of the choices, one of the things that you want to consider. The other one is locality.
Yeah,
Right?
that's right.
If you want to retrieve value from a vertex that is far away from the node that you're currently working on,
Yeah.
that is in a remote machine or something, then fetching data takes a lot of time.
That's right.
Right. So, do you have any plan on how to solve those problems?
Well, I think the key there is going to be the distribution of the data structures, the partitioning of the data
Right,
structures.
yeah.
So what you want to do is to try and make sure that you're operating locally as far as possible,
Right.
and then you
That's
need to
probably-
go remote
yeah.
only at the
Yeah.
boundaries.
You probably need your own like graph partition based
Yeah,
on
that's
particularly
right.
based on the
That's
algorithm
right.
that you're designing.
Yeah, so one of the things we've done is we've taken this popular Metis graph partitioner, and there's actually a Galois version of the parallel of the Metis graph partitioner implemented in parallel. So we also have a bunch of parallel graph partitioners written within Galois itself.
Okay.
Okay, good. Thank you.